Hello everyone, for today's video we're going to have the intercepts, zeros, asymptotes, and domain and range of rational functions. And the learning objectives are the following. Determine the intercepts, zeros, asymptotes, and domain and range of rational functions. But let us define first what an asymptote is. So when we say asymptote, it is an imaginary line to which a graph of a function gets closer and closer as it increases or decreases its value without limit, but it will never cross the graph. So it is an imaginary line. It will not touch the graph. Now, the graph of the function r of x is a continuous smooth curve with breaks that occur at the value of x where it is undefined. So you will find here a hole or a gap on the graph because of the values of x that will make the function undefined. So there will be a hole on that part of the graph. There are two types of asymptotes, the vertical and the horizontal asymptote. So to determine the vertical asymptote of a rational function, r of x, you're going to find the zeros of the denominator that are not zeros of the numerator. To find the zeros, all you have to do is to equate the factor of the numerator and denominator to 0 and solve for the value of x. That will be your vertical asymptote. Now, for the horizontal asymptote, you're going to compare the degree. When we're talking about the degree here, we refer to the exponent. So we're going to compare the exponent of the numerator and the denominator, and then we will represent the degree of the numerator by n and m by the degree of the denominator. Now, if the exponent of the numerator is less than the degree or the exponent of the denominator, then we only have the horizontal asymptote, which is the line y is equal to 0. Now, if we have the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is simply y is equal to a over b, meaning this is the leading coefficients. Okay, a and b are the leading coefficients of the numerator and denominator respectively. So that is the numerical coefficients. Okay, but if n or the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Okay, before we proceed to graphing, let us find first the asymptotes of the following. So we have here f of x is equal to 4x over 2x plus 1. So we're going to find the vertical and the horizontal asymptotes. Now again, the vertical asymptote is simply the zeros of the denominator that are not zeros of the numerator. So since we only have here 4x and 2x plus 1, they are different factors. So we will get the zeros of the denominator. So you will have to, you just simply equate 2x plus 1 to 0 and then solve for x. And that will be your horizontal asymptote. So that will be equal to the vertical asymptote, x is equal to 1 over 2. So this is now your imaginary line. Now for the horizontal asymptote, you're going to find or compare the degree. So we have here the degree is 1. So you have here 4x. So degree 1 here, also degree 1 here. So they are the same. So you're going to get the numerical coefficient. So you will have 4 and 2. So that will be 4 divided by 2 or a over b. So that will be y is equal to 2. So this will be your horizontal asymptote. Okay, compare the degree or get the numerical coefficients if they have the same degree. Okay, I hope that is clear. Let's have another example. We have here x squared over x minus 1. Again, since they have different factors, x squared over, you have x minus 1 here, so we get the vertical asymptote equating x minus 1 to 0. That will give us the vertical asymptote x is equal to 1. Now, for the horizontal asymptote, so we have here the numerator is degree 2 and the degree 1 sa denominator. So the degree of the numerator is greater than the degree of the denominator. So therefore, our horizontal asymptote is none. So we don't have an horizontal asymptote. Okay, since the numerator is greater, the degree of the numerator is greater than the degree of the denominator. Let's have another one. You have here this one. So here you will notice that this is a quadratic function. The first thing that you're going to do is to factor them. So you will have the factor for the numerator x minus 1 times x minus 3. And for the denominator, you have x minus 1, x minus 4. So we have here a common factor, x minus 1. Now this term or this factor that is being cancelled, meaning we have a hole on that part of the graph, which is x is equal to 1. There is a hole or butas. Now, to get the vertical asymptote, again, we equate the denominator. So, your vertical asymptote will simply be x is equal to 4. And then, for the horizontal asymptote, since they are equal, okay, the exponents are equal, so we will get the numerical coefficient. So, 1 divided by 1, that is simply y is equal to 1. So, that is the horizontal asymptotes of that function. For the last example, you have here x over x squared minus 4. So here, the factor is x, and then this one, we can factor this one, x squared minus 4 can be factored out as x plus 2, x minus 2. So equating this to 0, we will have now the vertical asymptote, x is equal to 2 and x is equal to negative 2. So meaning these should not be the values of x. Now the vertical asymptote, remember guys, is they are the values of x na that will make the rational function undefined. Okay? So the vertical asymptotes are also the points or the values of x that will make the function undefined. That's why your graph will have a break or a gap. Now for the vertical asymptote here, so the exponent in the numerator is 1 and in the denominator is 2. So since the numerator is less than the degree of the denominator, so your horizontal asymptote is y is equal to 0. So that is how you find the vertical and the horizontal asymptotes. I hope you get it. Okay, another term that we're going to need in graphing the rational function is the intercepts. So when we say intercepts, these are the points on the graph that crosses either the x or the y axis. Now the x-intercept of the graph of the rational function, if it exists, occurs at the zeros of the numerator that are not zeros of the denominator. So x-intercepts and vertical asymptotes are the opposites. Okay, they are opposites of each other. So x-intercept zeros of the numerator that are not zeros of the denominator, while vertical asymptotes are zeros of the denominators which are not zeros of the numerator. Okay, so that's why they are opposites. Or we can let the value of y equal to 0, and then we can solve for the x-intercept. Now for the y-intercept, all you have to do is to let the value of x equal to 0, and then we solve for the value of y, provided that r of 0 is defined. Okay, so that is how we're going to get the intercepts. Next is the zeros of a rational function. So the zeros of the rational function r of x is equal to p of x divided by q of x can be determined by solving p of x is equal to 0, meaning we're going to equate the factors or the expression in the numerator to 0 and then solve for that. Okay, so in other words, whatever values that make the numerator p of x equal to zeros are the zeros of the rational functions. Okay, so these are also the values of the independent variable that make the numerator 0, but it is not a restrictions of the rational function, meaning it is not the value of x that will make it undefined. Okay. Okay, let's have here an example. Find the intercepts and zeros of the following, or of the function f of x is equal to 4x divided by 2x plus 1. So first we find the intercepts. So to find the x-intercept, we simply let the value of y equal to 0. So f of x is also equal to y. So we equate them to 0 and then solve. So cross multiplication, we'll have 0 times 2x plus 1, that will be 0. So we'll have 4x is equal to 0. Dividing both sides by 4, that will still give us the value of the x-intercept, which is 0. So therefore, the coordinates will be 0, 0. So the x-intercept is 0, the value of y is 0, so we have the coordinate 0, 0. Now, for the y-intercept, okay, we will now let the value of x be equal to 0. So, this time, these are the zeros. Okay, so we replace this by 0. So, we will have now 4 times 0 is 0, and this you will have here 0 plus 1, so that is 0 divided by 1. Therefore, the y-intercept is also 0. And the coordinates is also 0, 0. Now, for the zeros of the rational function, these are the zeros of the numerator that are not zeros of the denominator. So, the zeros of the denominator is negative 1 half. So, we're going to equate for x by 0. So, this will be the zeros of the rational function is also 0. Okay. Okay, let's have another example. This one, again, you have x squared minus 4x plus 3 and x squared minus 5x plus 4. The first thing that you're going to do is to factor this out and reduce to lowest term. So, we can factor this out as x minus 1, x minus 3, and x minus 1, x minus 4. So, we cancel x minus 1. So, the reduced function will be x minus 3 over x minus 4. So, to get the x-intercepts, again, we let the value of y equal to 0. So, we'll be using the reduced form. So, we'll have here cross multiply again. This will be 0 times x minus 4 is 0. And then x minus 3 times 1, that will be x minus 3. And then, so the x-intercept here will be 3. Or we have the coordinates 3, 0. Now, for the y-intercept, let x be equal to 0. Again, using this one, so we will have 0 minus 3 divided by 0 minus 4, that will give you negative 3 over negative 4, or y is equal to positive 3 over 4. And the coordinates will be 0 and 3 over 4. Why do we have to get the coordinates? Because later on, as we graph the rational function, you have to plot these points. Okay? We get the intercept, but you're going to plot the points. Now, for the zeros of the numerator, or the zeros of the rational function, again, we simply equate the numerator of the reduced function x minus 3 to 0. So, that will be, the zeros of the rational function will be x is equal to 3. This cancelled one, x minus 1, or x is equal to 1, is the hole in the graph, or the vertical asymptotes also. Okay, I hope it is clear to you how to find the intercepts and the zeros of the rational function. To complete our graph, we will also be needing the domain and range of the function. So we discussed domain before as the set of all x values in the set, while the range is the set of all y values in a set, or in a relation. Now, for the domain of the rational function, that will also be the set of all possible values that the independent variable x can take, while the range is the set of all possible resulting values of the dependent variable f of x or y can take after we have substituted the domain. Okay, generally, the domain and range of a function is the set of all values for which the function is defined. Specifically, if we have a polynomial function, the domain and range is simply the set of all real numbers. For example, we have y is equal to x plus 3. So, this is a linear function. You can have any values for x and y. So, that's why it is the set of all real numbers. There is no restriction for a polynomial function, even if you have a quadratic function, a cubic function. Now, for a radical function, the number under the radical symbol must always be positive, or the radicand should be positive. For example, you have y is equal to the square root of x minus 1. If we substitute any values for x, the resulting value should not be negative. So here, for the resulting value to always be positive, we can have a x should be greater than 1. Greater than or equal to 1. So, we can have 0 but not negative. So, if we substitute greater than 1, for instance 2, so you will have 2 minus 1, that is still positive. So, all the values greater than 1 will be the domain. Same goes with the range. So, you just have to solve it. Now, for the rational function, which we will be dealing today, the denominator of the fraction should not be 0. So, for example, you have y is equal to 3 over x minus 1. So, the value of x here should not make the denominator equal. So, here, should not make the denominator 0. So here, the value of x cannot be equal 1. Since if you have 1, you will have 1 minus 1, so that will be 0. So your domain and range here, your domain specifically, will be any value but not equal to 1. So all real numbers except 1. Okay, so that is how we find the domain of irrational function. There is always a restrictions in the denominator. Here, there is a restrictions in the radicand, but for a polynomial, there is no restriction. I hope that is clear. Okay, let's have an example. Find the domain and range of f of x is equal to 5x minus 2 divided by x plus 1. Since this is a rational function, we can find the restrictions at the denominator. Okay, so to solve for the domain, you're going to solve for y in terms of x. And we know that f of x is also equal to y, so we can rewrite it this way. Okay, so since this one is already in y in terms of x, so we can now find the domain. By looking at the denominator, we know that x could never be or should never be equal to negative 1. So therefore, that negative 1 is the restriction. So your domain will be all real numbers except negative 1. Now, for the range, you're going to solve for y in terms of, solve for x in terms of y. So using this given, by cross multiplication, we will have y times x plus 1 is equal to 5x minus 2 times the denominator 1. So we will have it this way, or write it this way. And then using this derivative property, you will have y times x plus y times 1. So that will give you xy plus y is equal to 5x minus 2. Since we are solving for x, we transpose all the terms with x to the left side and transpose positive y to the other side. So you will have now xy minus 5x is equal to negative y minus 2. Looking at this one, you will notice that x is a common factor. So we're going to factor out x. So you will have x quantity y minus 5 will be equal to negative y minus 2. And then we divide both sides by y minus 5. So that will give us now x is equal to negative y minus 2 over y minus 5. And since this is already in x in terms of y, so again looking at the denominator, since this is a rational function still, so equating this to 0, we will have y is equal to 5. And that 5 is again the restriction. So your range will be all real numbers except 5, because 5 will make the denominator undefined. Your answer could be written in words just like this one, or you can use this symbol. This means that y, the set of all y's such that y is not equal to 5. And this one, you have the set of all x's or x, all values of x except negative 1. So you can write it in words or using this symbol. I hope that is clear. Okay, this ends our discussion. Please see the next video for the topic graphing rational functions. Thank you.